The first few questions are just asking about things we learned during the lab and in the lecture about acids, bases, and neutrals. So, is something purple with cabbage juice? Cabbage juice we know is purple normal, so that is a neutral solution. If the pH is greater than 7, 7 is neutral, greater than 7 is basic, less than 7 is acidic. Tastes bitter. Bitter is basic. Okay, acids taste sour. Lye. Lye was sodium hydroxide. And that was the chemical that was very, very basic. It actually turned yellow when we tested with cabbage juice. A solution that starts with H, okay, that's definitely giveaway that it's acidic, and HNO3 is actually one of our strong acids. And a situation where the H plus and the OH minus are equal, then that's definitely neutral. Now, Cn minus is a base. That is true, okay, the acid HCN. And if that donates a proton, then the Cn minus left over can be the conjugate base. It's definitely a base. It cannot donate an H plus. That's definitely true as well. But I wouldn't say that that explains why it is a base. There are a lot of things that cannot donate a proton, and it doesn't necessarily make them bases. So I would call this true. An aqueous solution of potassium chloride is a non-electrolyte. That's absolutely false. Okay, potassium chloride would dissolve very nicely because potassium compounds dissolve. Lots of ions, it would be a very strong electrolyte. And the salt dissolves completely in solution. That's definitely true. So that answer is false and true. Ammonia will turn blue-green in cabbage juice. We call it red cabbage, but it's really kind of purple looking. And that is true, and we just have to remember that from our lab. That was a base and did that. And its conjugate acid is ammonium. That is absolutely true, because if ammonia is a base and it gains a proton, it will look like NH4+. Okay, but that's not the reason why it turned cabbage juice blue or green. So it's a true statement. The solution could be considered. Okay, now this is odd because here we have particles, but could more particles dissolve in there? So it's really hard to say. So we don't know whether it's unsaturated or saturated. Also, there's the answer, is it cannot be determined from this. If there was stuff on the bottom, then we could say, okay, yeah, that looks like it's saturated because, everything has dissolved that can dissolve. But that's not the situation. Now, in our solubility curve, how many more grams of potassium nitrate, so this line here is the potassium nitrate line, can be dissolved in water at 70 degrees versus water at 40 degrees, and we're talking about 40 grams of water. So let's first just get our data from the chart. So at 70 degrees, it looks like the 130 grams of solute can dissolve per 100 grams of water. And at 40 degrees, look up here, and that says 60. So 60 grams at 40 degrees, 60 grams of solute can dissolve per 100 grams. So if we were using 100 grams, we'd say 130 minus 60, 70 grams would dissolve per 100 grams of water. But we don't have 100 grams of water, we only have 40 grams of water. So 70 is to 100 as x is to 40, and when we cross multiply, we're going to get 7 times 4 is 28, 2800 divided by 100. We can see the answer is going to be 28. Answer A. A beaker contains a saturated solution of sodium chloride in 50 grams of water. Beaker B has the same thing, saturated solution in 100 grams of water. So what is going to be more in B than in A? So this is 3 separate questions. So the ratio of the mass of dissolved NaCl to the mass of water, the ratio is going to stay the same. They're both saturated. The mass of solute particles, that will definitely be greater in B than in A, because we're going to have more particles dissolved in 100 grams than we would in 50 grams. And the molar mass of water, no, that's going to be constant. Molar mass of water is 18.0 grams per mole. And that's just oxygen plus 2 hydrogens. So the answer is B only. So on that kind of problem, you have to answer all 3 separately and then look for the right answer. Now for CO2, we have to know that CO2 is a gas, and gases dissolve the best at high temperatures. That's wrong. Okay, gases dissolve the best at low temperatures and at high pressures. So looking at the answers, we want to say, where does it dissolve the least? So we have to work backwards. We want not low temperature, we want high temperature. So the answer could be this one or this one. So let's knock off A and B. And we want not high pressure, we want low pressure. So that looks like that answer. So the answer here is C. We have to do a little mental gymnastics to work back. So we're watching for the least soluble. Which of these compounds is least soluble in water? Okay, least soluble in water. Well, what dissolves in water? Acids dissolve well in water. Okay, potassium carbonate, potassium compounds dissolve really well in water. And polar molecules dissolve well in polar water, because water is a nice polar molecule. Remember, it looks like a little Mickey Mouse, and it has a positive end and a negative end. So polar dissolves in polar, and we have to know that water is polar, and we should be coming into the test with that idea. So, like dissolves like, so the one who is least soluble is going to be the hexane, the nonpolar molecule. We would have two layers. Which of these compounds does not dissolve in water? Again, a negative question. So we got to eliminate everybody who does dissolve. Well, ammonium compounds dissolve really nicely. That's our solubility rules. Potassium compounds dissolve nicely. Nitrate compounds dissolve nicely. So the answer must be B, calcium carbonate. And if we look on our rules, the bottom rule, ones that hardly ever dissolve, carbonates. 16. What is the concentration of a solution made by dissolving 12 grams of NaOH in enough water to make 0.5 liters of solution? Well, we are doing molarity. So molarity, we know from our molarity triangle that the molarity is equal to the number of moles divided by the volume. So we want molarity equals moles over volume. Now let's look for our variables. Molarity, moles, volume. Now we know the volume is 0.50 liters, and that's good because it has to be liters. And we want to know the concentration, so we had to find moles. We're not given moles directly, we are given grams and molar mass, so we have to do a quick problem. So we say 12 grams, and we know that there's 40 grams in 1 mole. And if we calculate that out, we're going to get 0.30 moles. So go back here, substitute in 0.30 moles divided by 0.5 liters, and that's going to come out to be 0.60 molar. And that is answer A. List these solutions, okay, in the order of increasing concentration. That means we want the lowest concentration to the highest concentration. And that's always a little confusing, so I make a chart. Now, I have big volume and small amount. I can see I have two different amounts of solute, and I have two different volumes. So my smallest amount of solute in my largest volume, that's going to be my lowest concentration. Now of the other two, I've got a small amount of solute, and I've got double the solute in the same volume. So obviously double the solute in that same volume is going to be the most concentrated, and that leaves Y in between. So X is less than Y is less than Z, so we're looking for X, Y, then Z, and that's answer A. 18. A 100 milliliter sample of a solution with a concentration of 0.5 is diluted, 5 molar, is diluted by adding 300 milliliters. Okay, watch out for that. That's going to be important. Distilled water. What's the new concentration? Well, the dilution formula, the volume times the molarity before you dilute equals the volume times the molarity after you dilute. So what are our variables? Volume, molarity, and molarity. And our first volume, we have 100 milliliters of a sample with a 5 molar concentration. Now our new volume, this is the tricky because we're looking for a new concentration. It is not 300, and people who just look at a problem and grab the numbers are going to be in trouble here, because it says we're adding 300, so 100 plus 300 is going to be 400 milliliters. So we can see the problem is going to be 100 milliliters times 5 molar equals 400 milliliters times X. Solving for X, X equals 100 times 5 over 400. So we can see that 100 over 400 is going to be 1/4. 1/4 of 5 will be 1.25 molar. So again, be careful here. We're adding 300. It's not, the final volume is not 300. We're adding 300. So it's 100 and 400. Also notice that we do not have to use liters here as long as those units match, because they're going to cancel. If a solution that's a 0.1 molar solution of sodium chloride is spilled, what is the concentration of the remaining solution? So if you had a salty solution and you spilled some of it, the remaining solution is going to be just as salty as it was before. So this is a question to kind of get people who are just glance at the problem and then start throwing numbers into an equation. If you try to do Vm equals Vm, then you are going to get the wrong answer, because it's a thinking question. So if you spilled something, the remaining solution is going to be exactly the same concentration. Now, which of these is a base? Well, we can certainly eliminate H2SO4, that's an acid, and HC2H3. So things that start with H's, we know those are not bases. Of the other two, this one, B, this is an alcohol. And that's important to notice. It looks like a base because it has OH, but it's not. So when we have OH connected to carbons, that's an alcohol. We tested alcohols. Alcohols are non-electrolytes, and they were neutral. So that is not a base. This one is the base, a metal hydroxide. That is what's going to form a base, positive ion and an OH minus ion. So watch out for alcohols, that's a tricky one. A property of acids. Okay, so they feel slippery. No, that's a base. Bases feel slippery because they turn your oils into soap. They neutralize water. Nothing neutralizes water. It's already neutral. Acids taste bitter. No, that's a base. So there's two base things. And they taste sour. Yes, that's why we had sour candy, to show that the outside is coated with malic acid or fumaric acid or tartaric acid. So food acids taste sour. According to Sponte Arrhenius, acids, okay, so this is the Arrhenius definition of acids, and he says that acids increase the H plus ion concentration. So there it is, answer C. Answer D would be the definition of a base, and decreasing, that's not anybody's definition. So C is the right answer. Each of the following can describe an aqueous solution with a strong electrolyte. Okay, so who could be a strong electrolyte except... Okay, so it's a negative question, so we want to eliminate the ones that are strong electrolytes. So a solute dissociates completely into ions. Yes, that's going to be a strong electrolyte. A solution is a covalent compound. Let's come back to that. A solution is a strong acid. That's definitely an electrolyte. And the solution contains a large amount of ions. Okay, that's a strong electrolyte. So the answer must be B. And this idea that the solute is a covalent compound, something like we mentioned with our alcohol. If we had alcohol in water, okay, that we tested that, it does not conduct electricity because this does not turn into ions. So yes, that's the answer. A solute that's a covalent compound would not be a strong electrolyte. Okay, a substance that turns cabbage juice blue. Blue means it's a base, and only slightly lights up the light bulb. That means it's a weak electrolyte, so that's going to be a weak base. Weak base. Answer D. Strong acid or base would light the light bulb up a lot, and if it was acid, it would be pink or red, not blue. So weak base. Okay, a solution where the H plus is 1 times 10 to the minus 4. We know H plus times OH minus equals 1 times 10 to the minus 14, so the OH minus concentration is going to be 1 times 10 to the negative 10, because negative 4 times negative 10, that gives us negative 14. So we're looking for 1 times 10 to the minus 10. There it is. Answer B. 26. What's the hydrogen ion concentration, the H plus, of a solution where the pOH is 9? Okay, if the pOH is 9, then the pH equals 14 minus 9. Okay, so that'll be 5. So the pH is 5. That means that the H plus concentration is going to be 1 times 10 to the negative 5. We can do that in our head. And we're looking for 1 times 10 to the minus 5. There it is right there. So be careful. We're talking about pOH. Turn that into a pH and then to the H plus. Okay, which of the following may have a solution that's 8? Okay, 8 is going to be basic. So definitely we can eliminate acid, pool acid, and vinegar is an acid. And rubbing alcohol we said is neutral. We tested that. So the only one that's a base is ammonia. And we tested that in class. for the reaction, which is the conjugate acid? So let's take each one of these. We have to look at this in context. So when this changes to that, when the NH3 plus turns into NH2, that must have given away an H plus. So that is an acid. So therefore this is its conjugate base. And if this is an acid, then this one must be a base, and this must be its conjugate acid. So who is the conjugate acid? H2O. Which of the following is not a correct conjugate acid-base pair? The difference between a conjugate acid-base pair is just an H. So we're looking for a pair that only differ by an H plus. So looking at this A, this is a CH3OO minus and with the H, so this is okay, so that is not the answer, because that is a conjugate acid-base pair. Here we have two H's, here we have one H, so that is a conjugate acid-base pair, so that's not the right answer. C, H3O plus and OH minus. That almost looks correct, but it's actually the answer. And let's look at the last one, NH4 plus NH3. Okay, let's look at the, if I had water, okay, so water could give up an H plus and become OH minus. So that would be a conjugate acid-base pair. Water can gain an H plus and become H3O plus. So that would be a pair, that would be a pair, but they're giving us these two. So that is not a conjugate acid-base pair because it differs by two H pluses. And a good conjugate acid-base pair only differs by one H plus. Okay, which is going to have the lowest pH? You have to say to yourself, that is what is the most acidic. Low pH is acid, so the most acidic situation. These are all 0.1 molar, so concentration doesn't make a difference. We can look in the all-star with H. These are all acids. So the most acidic is whatever's going to have the largest Ka. The largest Ka is the most acidic. Now we have to look at these negative exponents, and remember that 10 to the minus 4 is larger than 10 to the minus 5, minus 8, or minus 10. So that is the large. So the answer A. Which of the following is the correct expression for Ka for the dissociation of a weak base ammonia? So again, we're not going to put in liquids. Liquids don't enter into this expression, so we can eliminate answer B and eliminate answer D. And it's products of a reactant, so we're looking for ammonia and hydroxide in the numerator, so the answer must be C. Okay, so the answer is C. Now, this has tiny problem in it, and that since this is a base, okay, Ka means the expression for an acid, okay, Kb would be for a base. So it's a tiny problem, but it doesn't change the answer. Okay, use the solubility curve to answer the following questions. So how many grams of potassium chloride, so potassium chloride, we're looking at this line here. Potassium chloride can dissolve in 80 grams at 80 degrees. So we look at our chart at 80 degrees. We can see that it's going to be 50 grams. So we get 50 grams of solute to dissolve per 100 grams of water, but we don't have 100 grams of water, we have 80 grams of water. So we can see that 50 is to 100 as X is to 80, and so X must be 40 grams. So 40 grams of solute would be able to dissolve. Now B, how many grams of potassium nitrate will precipitate out when a saturated solution with 600 grams of water at 80 is cooled to 50? So we know that 40 grams will saturate solution at 80. Okay, that's wrong. Okay, we'll go back to here. 50 grams will saturate 100 grams of water. So let's get our data. So at 80 degrees, 50 grams of the potassium nitrate. Oh, I'm on the wrong formula. Sorry. Okay, so potassium nitrate is this one up here, this line. So at 80 degrees, we can see that it crosses a line at 170. So at 170 grams will dissolve per 100 grams at 80 degrees. Now if we go down to 50 degrees, we can look at the chart here where it hits the line. That's going to be 80. So at 50 degrees, it's 80 grams per 100 grams. So we want to compare these two numbers, 180 going down, that's 170 going down to 80. So that's going to be 90 grams of solute would drop out for every 100 grams of water. So now let's get our answer. So if I had 90 grams would drop out per every 100 grams of water. We have 600 grams of water. So I want to solve for x, so we can see I just have to multiply 90 times 6, and that's going to be 540 grams. So 540 grams of this solute would drop out of solution. So we have to use our chart, and then we have to always do like a proportion to take into account the fact that it's 600 grams of water, not 100 grams of water. What is the concentration of a solution when 0.4 moles of KBr are used to prepare 600 milliliters of solution? Okay, now when we do concentrations, we are always going to be doing liters when we use the molarity formula. So I immediately change that to 0.6 liters so I don't get confused later. Now molarity is number of moles over the volume. Okay, so my variables then are molarity, and I'm looking for that. Number of moles, and that is 0.4. And volume, and that is 0.6. So we can just substitute in. So 0.4 over 0.6 is going to be 2/3, okay, 0.667 molar solution. How many grams of calcium nitrate is needed to prepare 120 milliliters of a 0.150 molar solution? Okay, so let's go back to our molarity triangle. And for our molarity triangle, we know molarity is equal to the number of moles divided by the volume. And we want to find, what do we have? So we have molarity, we have volume, we have number of moles. Okay, we're given the molarity, so we know this is 0.150 molar. And the volume, 120, we're going to change that to 0.120 liters. So we have to find the number of moles. And then we're going to, since we're trying to get grams, we're going to change grams to moles. So we have an extra step after we find moles. Well, using our molarity triangle, we can see if I want to find moles, then I'm going to need to do the molarity times the volume. So molarity is 0.150 molar, moles per liter, times 0.120 liters, and that equals 0.018 moles. So that's my middle answer. Now I need to change that into grams, and grams of calcium nitrate. So we're going to have to take a moment and take out calcium, and we're going to have 2 nitrogens, and we're going to have 6 oxygens. Calcium weighs 40. 2 nitrogens would be 28, 6 oxygens would be 96, and when we add that all together, we get 164 grams per mole. So my last part of this question is going to say, okay, 0.018 moles of my solute of calcium nitrate, and for every 1 mole, I know that weighs 164 grams. And so my final answer here is that I'm going to need 2.95 grams of my solute. So I use my molarity triangle to figure out moles, and then I have to do stoichiometry to go from moles to grams, and I had to actually figure out the molar mass of calcium nitrate. Okay, 35. How many milliliters of 6 molar HCl solution are needed to prepare 120 milliliters of a 0.8 molar solution? Okay, so we can kind of see we are diluting. So our equation is going to be volume times molarity before we dilute equals volume times molarity after we dilute. So let's get our variables, volume and molarity, volume and molarity. And the key piece right here is to find the volume and molarity that go together. So I say how many milliliters of 6 molar, so those get together, to give 120 milliliters of 0.8 molar. So now we just substitute in, so x times 6 equals 120 times 0.8, and when I solve for x, I have 120 times 0.8 divided by 6. When I do that, it's going to give out 16. Now, notice what happens is that I was using milliliters here, so my answer comes out in milliliters, and these are both molarities, so the molarities cancel, and I'm just left with milliliters. So 16 milliliters of my concentrated solution. I could dilute that to 120 milliliters, and my new molarity would be 0.8. Now for 36 here, we are doing pHs and pOHs. Now the first step here, we have 1 times 10 to the minus 1. Okay, so I know that my pH is 1. I can do that in my head, and I would say that that's actually 1.00. Two significant figures gives us 2 decimal points. Now if I know my pH, I know that my pOH is 13.00 because pH and pOH always add to 14. Now right now, since I know my pH and it's less than 7, then I know this is an acid, and I only figure that out from my pH. And the last step is the H plus concentration must be 1.0 times 10 to the negative 13, and I can say that it's 10 to the minus pOH, 10 to the minus 13, or I could take this number divided into 1 times 10 to the minus 14 to get this answer. But that's the first one. I'm given 4.8 times 10 to the minus 3, so I can take the negative log of that and get my pOH, and I know it's going to be somewhere between 2 and 3. So using my calculator, I find out that this is 2.32. Now, pH and pOH always add up to 14, so subtracting from 14, I find out this is 11.68. I have two choices for how to do this one. This is either going to be 1 times 10 to the minus 14 divided by this number, or I can take 10 to the negative 11.68. Either way, I'm going to get 2.1 times 10 to the minus 12, and I definitely need my calculator to do that. Looking at my pH, that's greater than 7, so I know that this is a base. Okay, pH is 6.2, so subtract from 14, so I know that my pOH must be 7.80. Now I can take 10 to the negative 6.2, and I get 6.3 times 10 to the minus 7. And if I take 10 to the negative 7.8, I get 1.6 times 10 to the negative 8. Now again, 6.2 is less than 7, so I know this is an acid solution. And the last one, if I know that my pOH is 10, then this must be 4, because they add up to 14. Okay, the H plus is 10 to the negative 4. 1.0 times 10 to the negative 4. And the other one here must be 1.0 times 10 to the negative 10. We can do all that in our head. And pH is less than 7, so again, this must be an acid solution. Find the pH of a 0.015 molar HNO3 solution. That is a strong acid. So I know that my HNO3 is going to completely break up into H plus and NO3 minus. So whatever my concentration of HNO3 is, that's also going to end up being my concentration of H plus. So I just need to take the negative log of 0.0150, which is 1.5 times 10 to the negative 2. So I know my answer is going to be between 1 and 2, and the pH turns out to be 1.82. You need to use your calculator. Given this benzoic acid, so HC7H6O2, double arrow, we get H plus, and whatever's left over, C7H6O2 with a minus charge. Okay, that's my expression there. That's my equation. It's a minus. And then my Ka expression is going to be concentration of H plus, concentration of C7H6O2 minus, all over HC7H6O2. Okay, and I'm just about to run out of time, so we have to realize that the next step here is to do an icebox. You're going to have to look at the answers to see this. Do an icebox for this, and you're going to calculate the H plus concentration. From that, you can figure out the pH, and then subtract from 14 to get the pOH. And the percent dissociation is going to be X over the initial value times 100, and you can check the answers to see how that comes out. And the last one is this potassium sodium phosphate, so Na3PO4, because we know our ions, we know PO4 is 3 minus, and so the concentration will be the 3 times this number for the sodium and the same number for the phosphate. That's it.